In this video, we're going to consider inverse of functions, how to find them, how to graph them, and how to check if two functions are inverses of each other. So a couple of things. We say that the inverse of the function, for example, f of x, is written as f with the exponent of -1, x. So f with the -1 exponent of x, that's how we write the inverse of the function f. Now, this is not to be confused with something that looks like this, which would mean that I would write this function as 1 over f of x. That is an actual exponent. This is just a notation. So do not confuse the two and do not use this notation. Now, in plain English, how do we do this function? The best and easiest method of doing it is just by flipping or reversing the x and the y's of a function. And once you do that, you get the inverse of the original function. Now, before we do an official definition, let's look at an example. So we're given the function f of x equals x plus 1 squared plus 2. So if I was doing that numerically, all I would need to do is plug in a bunch of values for the f of x function. So this is for the original, the first graph. So hopefully you remember the features of functions. The vertex for x plus 1 squared plus 2 would be -1, +2. So I would put that in the middle of my table, -1, +2. Once I do that, I would just go with the x values in both directions. So 0, 1, 2, -2, -3, -4. And I would plug in those x values in the original f of x function. And I would get, when I plug in 0, 1 squared plus 2, we get 1 squared, which is 1, plus 2 is 3. And you just do that with all these x values to get your f of x values. Now, once you've found the y values in one direction of the vertex, we know it's symmetric, so I'm just going to copy them in the other side. Now, these are my values for the f of x function, and now all I have to do is find the inverse function. And again, for the inverse function, you just flip your x and your y values. So my y values for my original function just become my x values. So my x values would be 11, 6, 3, 2, 3, 6, and 11. And then my y values for my inverse function would just be my original x values, which would be -4, -3, and so forth, all the way to 2. And that's all you would have to do if you're trying to find these values numerically. Now, how about if I'm given a graph? Or if I'm given the function, I can graph the original function in the same way as we just kind of did these tables. So if you look, the f of x function is the same as the graph I'm originally given. And I have those same values for those points. Now, what if I didn't have this table? I could easily just look at these points and I would find these coordinates. So this coordinate is -1, 2, and I would just reverse that to 2, -1. And here's my first point. Now, make sure if you're doing this graphically or numerically that you're finding your key points like your vertex and a couple of points in each direction away from your key points so you can make sure that you have a full picture of the graph. So again, I would just find a couple of other important points on the graph, and those would be it, and I would just reflect them. So I would flip the x and the y values. So I would have 3, 0, and 1, 6, 1 from the 1, 6. And then from -2, 3, I would have 3, -2, and I would also have the point 6, -3. Connect these dots, and this would give me my inverse function. Now, a couple of things that I want you to notice. The original function was actually a function, and the way we could easily know that is because it passes the vertical line test. So no x's repeat, right? So if you were to draw vertical lines right there, it passes the vertical line test, and the original function would be a function. The original graph was the graph of a function. However, if I look at this inverse graph, you can see, oh, I crossed 2 points. So at most of the parts in this graph, I would cross 2 points. So my inverse is actually not a function. So it's the inverse of the original equation, but it is not a function. That's okay. You can still find the inverses. It would just not be a function. But an easy way to know this from the original is if you look at the horizontal line test, it does not pass it. So the horizontal line test, the way we would look at it is if you draw a horizontal line and it crosses more than 1 point, so 2 or more, then you know the inverse is not going to be a function. So if a original graph passes both the vertical and the horizontal line test, then we would say that function is 1-to-1, which just means that the inverse will also be a function, and every x has only one y value. So let's look though at how we would write the inverse for this function algebraically. So the steps are given to the right, and the first thing you have to do is just to replace that f of x value with a y. So the first step, just write the original equation in this manner. So I replaced f of x with y. Then the second step says to swap the x and the y variables. So instead of y equals, I write x equals. And instead of x, I replace x with y. So y plus 1 squared plus 2. Now I have to solve for the new y variable. So here's my new y variable, and I have to basically undo the plus 1 squared and plus 2 by undoing the order of operations. So first thing I need to get rid of is I go opposite of GEMDAS or PEMDAS. So I subtract the 2 from both sides, and I get x minus 2 equals y plus 1 squared. And now I have to get rid of the squared. Now, to get rid of a squared, you have to square root both sides. Now, one important thing that we have to consider here is when you square root something, you have to add plus or minus to the side where you're not getting rid of the square root. So right on the left side, we're going to keep that square root. On the right side, the square root will cancel out with the square, so I'm just going to be left with y plus 1. The reason this is, if you remember, if, for example, had x squared equals 49, then my x could be either positive 7 or negative 7, right? Positive 7 squared gives me negative 49, and negative 7 squared gives me 49. So therefore, when I do x equals, I need to do plus or minus 7. I have two possible solutions because both positive and negative numbers give me the same answer. So that's why we need to include that plus or minus. Now this leaves us with plus or minus square root of x minus 2 equals y plus 1. And now I need to just subtract the 1. Now notice I put the minus 1 at the beginning. That way I know I add and subtract the square root of x minus 2 from both of them from negative 1. So I get negative 1 plus or minus square root of x minus 2 equals y. And then I just have to do the last step, which means I have to write it as f of negative 1x. So the inverse of that function equals negative 1 plus or minus square root of x minus 2. So I basically have two equations. I could also write this like this, plus or minus square root of x minus 2 minus 1. So if you just think about it, this just means I have x minus 2 minus 1, so one square root function, and the reflected square root function. And if we look at this original function, it makes sense that I have two different equations, two different square root equations. One is here above the x-axis. This would be the positive square root of x minus 2 minus 1. And then this one is the reflection of that equation of x negative x minus 2 minus 1. We can also look that the domain of the original or red function is negative infinity to infinity, and then the range for the inverse function is also negative infinity to infinity, while the range for the original function was from 2 to infinity. That is the domain of the inverse function from 2 to infinity. So let's write that out, as well as what are the x and y intercepts for the original function and its inverse. And if you notice, the domain and the range flips. So the x and the y, right? The domain is just all possible x's, flip with all possible y values for the inverse and so forth. So you need to always make sure that you have checked that your domain and range have flipped correctly. And if not, you might need to restrict your new domain and range depending on the original given function. Now, let's look at a little bit of these functions and see, do they have any sort of reflections? So if I'm gonna give you guys 3 sets here of functions, and if you look at the equation y equals x, so this imaginary line here, you'll see that the two lines that I gave you that are inverses of each other are reflected over that imaginary line of y equals x. Same thing with these two inverses, right? Both of those are reflected over y equals x. So we can use that to our advantage, because if we are to calculate f of x and g of x, let's see what we get. So if I calculate f of g of x and I graph that, I see that's also equal to x. And if I calculate g of f of x, that's also equal to x. So both compositions of functions should give me x, and as long as both work, then we say those two are functions. Let's look at one more example. So m and n, and those are my two functions. Let's look at both compositions. You'll see they're both equal to x. So that is part of our official definition, where both, to check if two functions are inverses, you have to do both compositions and they must both equal to x. So looking at this example, let's prove that f of x and g of x are inverses of each other by plugging in g of x into f of x and f of x into g of x, and showing if they are both equal to x, then they would be inverses of each other. So all I did was, first I'm going to find f of g of x, and all I did was replace this x value with g of x, which is x minus 3. So now I need to just simplify this, and I can simplify negative 5 plus 5 since there's both under the cube roots. So that leaves me with cube root of x cubed, and cube root and cube just simplify and cross out. So I'm left with f of g of x is x. So this one is good. And now I have to do the same thing for g of f of x. So as you see, I wrote g of f of x, and I replaced f of x with cube root of x plus 5. And then I used that to replace the x cubed and g of x with the g of x. And now I need to just simplify as we did before. Cube root and cube cancel out, so I'm left with x plus 5 minus 5. 5 plus 5 is 0, so I'm just left with x. So g of f of x is also equal to x, so we can say these two are inverses. So we can say g of x is equal to f negative 1 of x. So for an equation g of x to be the inverse of f of x, that only occurs if both f of g of x equals to x as well as g of f of x equals to x. And for g of x to be a function, f of x must be 1 to 1, which just means that each x has only one y, and the f of x function passes both the vertical and the horizontal line test. Now let's go practice inverses.